couple videos, we've taken a look at the response of first-order systems and of second-order systems. So now what we're going to do is we're going to take a more general approach to analyzing general systems from a state space point of view and the response due to exponential inputs. And so that may seem like a pretty limited class of inputs, but there is a lot more expressive capability. When we take a look at our input, it's not just, say, e to the 2t that we could choose. There are a couple special cases, one of which is when s is equal to 0. When s is equal to 0, now this becomes a constant input, and so that represents or can take the place of a step function. At the same time, if s is a complex number or imaginary, then you could get some sinusoidal or oscillatory kind of behavior. And so both constant and oscillatory, these are both really two very important types of inputs, especially when we look at control systems. So that's why this is particularly useful. It's also particularly useful because we're able to analyze this quite nicely mathematically. So what we're going to do is we're going to start with our solution y of t as a state space solution, and we're going to plug in this exponential input into the two places where u appears in that solution. And so this next step seems rather intuitive. Essentially, we're going to take this piece of at, because that's not dependent on the integrand tau, we're going to pull it outside, and then we're going to combine this piece of the exponential, the minus a tau and the e to the s tau. We're going to combine that into the same exponential. But to be particularly rigorous about that, we need to show a few things. And so that's what I'm going to do on the next slide, and then we're going to come back and finish this slide. So this is where we started. So I'm just taking a piece of it, and this is where I claim that we get to, and it takes a few steps to get there. So the first bit is that we can separate this exponential into a term that we can pull out of the integral, because it's a variable is t, and so that's not the integrand. And then a piece of the exponential that goes still has to stay inside because it's a function of tau. So keep in mind that A, since it's a matrix, it's an n by n matrix, that makes this a matrix exponential, which means that this quantity e to the minus a tau is a matrix. Whereas this exponential, e to the s tau, this is a scalar, because s is a scalar and tau is a scalar. So when we combine them, we have to be a little bit careful about how we end up doing that. And so the other important thing is that this is a matrix, B is a matrix, and this is a scalar. So what we have to do is we have to be careful, because you can't always swap the order of matrices. So AB is not BA. In fact, most of the time you can't do that. It's special cases when you can. So let's see how we do this kind of from a very systematic, rigorous point of view. So let's take a look at this particular quantity that's now inside the integral. So what we're going to do is we're going to go ahead and insert the identity matrix in here. So this is a little trick that we use a lot to essentially take something that is a scalar and make it into something that ends up being a matrix. So the one special case is that order switching, as the identity is commutative, so that means it can move around, and a scalar can also move around. So a scalar can be brought inside like this. It can move around because it doesn't, the order doesn't matter in matrix multiplication when you're dealing with a scalar. So now that we've swapped this in, now we have this quantity, and now the important thing to realize going from this step to this step is that these two exponentials are the same. So essentially, this comes from the fact that this is a diagonal entry. So in this case, this I just looks like this, and then all we're doing is we're going to put e to the s tau on each of these entries. E to the s tau, e to the s tau, so that replaces the one. We're multiplying that, so we just get a diagonal matrix of e to the s tau when we multiply the identity times that quantity. And so that is the same thing as taking the exponential of a diagonal matrix that goes like S tau on all the diagonals. So, and that's what we're saying here. So that allows us to get these two different pieces, and then when we add those or combine those together because of this matrix multiplication, now we recover this quantity that's in the integrand. Okay, so now that we've substituted u into both of these spots and rearranged this set of exponentials into a piece that comes out in front and the piece that's inside, now what we're going to do is we're going to make an assumption about the value of s, and in this case we're going to assume that it is not an eigenvalue of the matrix A. So from the transfer function point of view, that means that it's not a pole of the original system. So if that's true, then this inverse exists, and that's important because if we want to go ahead and evaluate this integral, we're going to need this quantity to exist. So let's assume that that's the case, and now we're going to have this product, this inverse multiplied by this exponential, and then this inverse multiplied by I, and that'll spread it out. So that's all of our terms. And then the last thing that's worth explaining is the fact that when you have an exponential like e to the at, ae to the at is e to the ata. And this is one of those special cases where matrices do commute. So A is a matrix, e to the at is also a matrix. And if you write out the exponential in its Taylor expansion, that allows you to prove that if you pull A out from the other side, it also works. So this is a special case where the matrix commutes with this exponential, where that same matrix is in the exponent of the matrix exponential. So that gives us the opportunity to commute this. This particular works because it's not only the matrix A, but it's also the identity, and so that's what makes that particularly easy. So now that we've done all that manipulation, the insight that we get is two different ways of writing this expression. So what we can do is we can either write the things that are dependent on the initial condition, and then the rest of it that's dependent on the input. And so the input essentially comes in all of these blue terms here. So that's the input response. And this is what happens because of initial states. And so this, remember, we saw something similar to this from the homogeneous case. The other way to write this is to observe that, for example, imagine in the case where your system is stable, that there is a transient response. There's something that's depending on time, but it's decaying away. And so this matrix exponential e to the at is something that if A is stable, if that whole system is stable, then this is a decaying exponential. And so this is a piece, this purple bit here is a piece that represents behavior that happens, but that slowly fades away over time. And what you're left with is something that's constant. And again, this is no longer a function of time. It's a constant, and it could be, for example, if it's a sinusoidal input, if S is complex, then this could be something that's varying because the response to a sinusoidal input would have oscillation in steady state. So if it was a constant, then this would be e to the 0t. That would be, then this quantity would be a constant. We'll take a look at that in a little bit more detail. But essentially, this represents what happens to the system after all the transient behavior, all this stable stuff would have decayed away. Now, the transient response is not doesn't go away if A is unstable. So that's also an important point to keep in mind. But it's insightful to kind of look at the two different ways you can interpret this solution, either from an initial state response versus an input response, or a transient response versus a steady state response. We've made a few mentions in the course about zeros, and so if we were to write our transfer function, so this could represent just about any sort of transfer function, we called the the zeros, or the roots of the denominator, let's call them the roots of the denominator. These are these pj. We call these the poles, and the roots of the numerator, essentially these zi's, these are the zeros. And so we're going to start talking about those more and more because they play a larger and larger part of the overall dynamics. But fundamentally, remember that it is the poles that are in the denominator, and these ultimately are what shape the type of responses, the exponential, the sinusoids, and so on. These zeros, z's, factor into these different coefficients that are in the numerator. So they represent essentially how much of each of these modes exist. And so these c's, these coefficients that are in the numerator, these aren't always simple expressions. They could include the z's, they could include the poles as well. But it's the role that these z's play, the zeros, is in shaping these different coefficients, and ultimately that tells you how much of these different modes you have. And so another way, just to be particularly clear about this, especially in the context of exponential inputs, is to say, okay, I'm going to evaluate my transfer function at a particular complex value where s is equal to zi. And so if you plug in s is equal to zi up here, you notice that there's a term here, one of these product terms, that becomes 0. And so that means that the result is 0. And one of the ways to interpret that is the fact that if you have an output that's going through a block with transfer function g that has a 0 at zi, and you inject an input that is an exponential at that s is equal to zi. So now you're saying this exponential, its exponential characteristic constant here, s, is at the same place as one of your zeros of your transfer function here. That means that the resulting output is 0 because of this. And so one way of interpreting a 0 is the fact that they denote the exponential inputs that are effectively blocked from reaching the output. So you inject some sort of exponential input. It could be, it could be an normal exponential input. It could be some sort of complex exponential input. It could be a step input, but that effect of that input doesn't reach the output because the output is 0. And so that's part of the reason why it's called a 0 of the transfer function. And the last thing we're going to do is just to look at a little bit more carefully the step response. So that's where our exponential input has s is equal to 0. So in that case, we had s's appearing here. That's the most important aspect here. S also appears here. And so what ends up happening is, s also appears here. Then what ends up happening is that our complete solution gets simplified into this value, which is a constant value, and this piece, which this internal bit is constant, and then this is a exponential either decay or oscillation or oscillatory decay, or if it's unstable, then it's exponential growth. But so if A is stable, then this piece goes away, and that represents the transient response, and this then is the steady state response. And so we're going to see lots and lots of different plots that look like this, which is the characteristic step response of a second order system. And so what we're going to talk about next in the next activity is quantifying some characteristic quantities that we can use to evaluate kind of the goodness of a step response. And so we can characterize things like how long it takes for the system to respond, that's this rise time, how long it takes to reach its peak time, how much it overshoots the steady state value, and then how long it takes for essentially the wiggles to wiggle themselves out. And so that's our settling time. So in the context of our exponential response, this gives us a nice closed form solution for how the state space variables or state space matrices, C, A, and B, and D all factor into both the transient response and the steady state response. And so if we think back to the second order case where we had solutions that looked like C1 plus C2 times e to the P1t plus C3 times e to the P2t, here we had our transient response, and here we had our steady state response. If these P1 and P2 are stable, these go away after some amount of time, and we're just left with this constant term. And so now we're seeing a very similar thing, in fact, exactly the same thing, play out in the state space representation, just from a different perspective.